Let's do a few more examples of seeing if either an atom or an entire molecule is chiral. So here I have a molecule. Let's see if we can identify any chiral centers or any chiral atoms or asymmetric carbons, all words for the same thing. Although I guess you could have chiral centers that aren't necessarily carbon, but it tends to be carbon most of the time, especially in an organic chemistry class. So if we look here, the one that kind of jumps out, this carbon right here is bonded to 3 hydrogens and another carbon. So this is obviously not going to be a chiral center. It's bonded to 3 of the same group. These 3 guys are all bonded to 2 hydrogens each. So they're all bonded to 2 of the same group. So they can't be chiral centers. This carbon right here is bonded to 3 hydrogens. Once again, 3 of the same group, not going to be a chiral center. This one looks interesting. Looks like it could be a good candidate for a chiral center or a chiral carbon or an asymmetric carbon. Over here on the left, it's bonded to a methyl group. So this is a methyl group. And here on the right, it's bonded to a butyl group. Here on the right, it is bonded to a butyl group. It is bonded to a butyl group. Over here, it's bonded to an OH, and then over here, it's bonded to an H. So this is definitely a chiral carbon. We could put a little asterisk here. That's how they often denote that this is a chiral carbon. And if this doesn't make sense to you, because you might say, hey, Sal, look, this carbon is bonded to 2 other carbons. Isn't that the same thing? But the point here is that we're not looking at what atoms it's directly bonded to. We're looking at the groups that it's bonded to. In this case, this hydrogen is a group and an atom. Over here, it's an entire group. It's an entire butyl group. We have 4 carbons here. We only have 1 over here. Another way to think about it, we could have drawn this molecule like this. We could have had a carbon in the center, and maybe this methyl group is popping out like this. So maybe this methyl group is popping out like this. You have your CH3, and then you would have this hydrogen coming out maybe in the plane. And then behind it, you would have the butyl group. So kind of the back leg of the tripod, you'd have a butyl. And what is that? That's C4H9, right? That's 6 plus C4H9. So it's C4H9 in the back. And then above it, you have your OH. Above it, in a different color, you have your OH. And when you look at it like this, it looks just like the other chiral carbons that we had identified in actually the last video. It looks very similar to something like this. And when you take its mirror image, this and this is the same molecule here. I kind of made it a little bit more three-dimensional. But if you take the mirror image of either one, you're going to find that no matter how you try to rotate it or shift it, you won't be able to superimpose it on its mirror image for the same reasons as the other ones. And I challenge you to if you can. So this is a chiral carbon. This is a chiral center, we could say, or we could even call it a asymmetric carbon. It could be considered a stereo center or a stereogenic center. All of those are valid things to call this carbon right there. And this is also a chiral molecule. This is also a chiral molecule. Chiral molecule. Now let's look at this blue example right here. And just as if we wanted to name it, just so we get a little bit of review, we could start at this fluorine right there. 1, 2, 3, 4, 5. 5. This is what? This is 1, 3, 1, 3 difluoro cyclopentane. So that was a nice review of naming. But let's think about whether we have any chiral centers here and whether the molecule as a whole is chiral. So the immediate ones that we can kind of dismiss, and actually let me get rid of this numbering here just because I don't want you to think that there are somehow 3 hydrogens there. This is the number, that was the number 3 hydrogen, number 3 carbon, number 2 carbon, so on and so forth. But let me get rid of them now that we've named the molecule. Don't want to confuse how many hydrogens we have at any of these points. So let's look at the carbons. Well, we can immediately dismiss that carbon, and that carbon, because each of those are bonded to 2 hydrogens. If we wanted to break it out, they would look like this. So they're bonded to carbons, and then they're bonded to hydrogens. Now, these might be different groups. These might be different types of alkane groups that it's bonded to. So that doesn't necessarily throw it out of the running. But these two, the two hydrogens that it's bonded to, are definitely the same atom, the same group. We have an axis of symmetry through that atom. So it cannot be a stereogenic center. It cannot be an asymmetric carbon. It cannot be a chiral center or a chiral atom. So we can knock those guys out of the running. But this guy and that guy seem pretty interesting. Because if we were to break it out a little bit, you could break it out like that and break it out like that instead of writing a CH, actually show the bond to the hydrogen. And this guy is bonded to one hydrogen, one fluorine. And then if we were to work our way around the cycle, and these cyclic molecules are a little bit, it's sometimes a little tricky to identify whether you're bonded to the same group or different groups. But actually, let me not make it too messy while we try to figure this out. To figure out whether it's bonded to the same group, let's kind of take a walk around the cycle, around the cyclopentane ring. If we go this way, if we go in a counter, let me do a different color. If we go in a counterclockwise direction from the carbon in question, we're going to hit a CH2, then we're going to hit a CH. So we're going to hit a CH2, then we're going to hit a CH. If we go this way, we're going to hit a CH2, and then we're going to hit another CH2. So this guy is fundamentally, this bond is bonded to a different group than that bond up there is. And it's also bonded to a hydrogen, also bonded to a fluorine. So this is bonded to 4 different groups. So this is a chiral carbon. So that is a chiral center. Chiral center. Now, the exact same argument can be made for this carbon right here. You can make that exact same argument that, look, if you were to walk counterclockwise from this, or if you were to write counterclockwise, you'd hit a CH2, then a CH2. If you were to go clockwise, you'd hit a CH2, then a CH, which happens to be connected to a fluorine. So you're actually going to see something different depending whether you're going down that into that group or into that group. And then it's also bonded to a hydrogen and a fluorine, 4 different groups. This is also a chiral center. Another way to think about it, and it's actually interesting to compare it to this molecule up here, which was not chiral and did not have a chiral center. This molecule up here, and let me draw it a little different to make it a little bit more clear. Let me draw it a little bit different. So this one I can draw it like this. I'm just making, if you have the chlorine like that. Over here, we thought about this as a potential chiral center, and it's kind of playing the same role as in that example down here, as in this example of this carbon down here. But you see over here, this is not a chiral center because there's actually an axis of symmetry for this molecule that goes through that carbon. So you can actually just draw an axis of symmetry that goes exactly through that carbon. It's not, the way I drew it, it's not completely neat, but you can see that that is the reflection of that if I were to draw the bonds actually a little bit more symmetric. Over here, if we try to do the exact same thing, if we try to draw an axis of symmetry over here, we try to draw an axis of symmetry, we can make that bond to the fluorine go through our axis of symmetry. We'll see that this is still not the reflection of this because we have a fluorine up here. We don't have a fluorine over here. And we could do the same thing with this end. If you try to do an axis of symmetry, fluorine up there, no fluorine over here. So each of these are definitely chiral centers, while this carbon up here was not a chiral center. Now, the next question is, well, this thing's got 2 chiral centers, 2 chiral carbons. It's probably a chiral molecule. Everything else we've seen so far, if you've had a chiral center, you had a chiral molecule. But let's take its mirror image. Let's take its mirror image. And to take its mirror image, let me clear out some real estate over here. So let me clear out this. Let me clear it out. So what's the mirror image going to look like? So we have, let me draw first the mirror. Let me first draw the mirror. So the mirror image, you're going to have a fluorine over there. Then you're going to bond to a carbon, which is also bonded to a hydrogen. Then that's going to bond to a CH2. That's going to bond to a CH. That's the mirror image of that, which bonds to a fluorine. That's the mirror image of that. And then you go down. This is the mirror image of CH2 here. This is the mirror image of this. And you connect them. Now, these are mirror images of each other. But they are also the exact same molecule. I could just literally move this guy over to the right, and it would be superimposed. They are exactly the same. So even though we have two chiral atoms, two chiral carbons, the molecule as a whole is not chiral. So it's not chiral. It is a non-chiral molecule.